Recall that in the last couple of videos, we've been discussing techniques to estimate the parameters of an ARP model. In particular, we've talked about the Ewell-Walker technique, and we've talked about the least squares estimation technique. In this video, we'll talk about the Burg estimation technique. Now recall that the one drawback for the least squares estimation technique was the fact that we felt like we left some information on the table. That is, we didn't significantly use the data values x1, x2 out to xp in a way that we feel that we probably should have. And we mentioned in that video that the Burg estimation techniques does take advantage of that. Now, before we jump into this though, let's recall that the correlation structure for an ARP model is such that it can look into the future just as well as it can into the past, and that correlation structure stays the same. Now, that may not have much physical meaning because whenever we can't look into the future, but mathematically, that correlation structure stays the same, so it is equivalent information, and this Burg estimation technique is going to take advantage of that fact. Now, let's go to the model because our model looks different. We're going to call this model the backwards model because it's opposite of what we had before, because before we would look at values in the past. Now, though, we're going to look into the future. Let's look at this formula and you'll see what we're talking about. X sub t equals phi 1 times x sub t plus 1 plus phi sub 2 xt plus 2 all the way out to phi sub p times xt plus p plus delta t, a little bit different name for our error term, for the noise term. So that is our new model. So let's list out some terms. X of 1, if t is 1, we have x sub 1 equals phi 1 times x sub 2 plus L2 phi p times x 1 plus p plus delta 1. Let's go to the next term. X sub 2 equals phi 1 times x sub 3 plus out to phi p times x 2 plus p plus delta 2. And that keeps going until we're down to, we can only go to n minus p. The advantage of this model as opposed to our least square setting was, remember, we couldn't do x1 and x2. We could only get started at p plus 1. But this model, the good news for this model is it can start at x1, x2, x3, but it can't go past n minus p. So we're going to have to stop this at n minus p, where we will have phi 1 times x sub n minus 1 plus all the way to phi p times xn plus delta n minus p. So this is our set of equations, and just as we did in the least squares technique, we're going to be thinking along the same lines here of trying to minimize these noise terms, minimize the deltas, just as we minimize the A's in the least squares estimation technique. So what we want to do now is we're going to call these, remember for the least squares, we had called these error terms, they were A's, right? And our goal was to minimize SC, C for conditional, which was the sum of the A hat squared T's, where t went from p equals 1 to n. Well, now what we want to do is we'd like to minimize these. We'll give them a new name. We'll say SB for backwards. And we want to minimize the delta hat, t squareds. And those go from t equals 1 to n minus p. So the goal then is to minimize the sum of both of those. So SC plus SB. These are called the forward-backward least squares. And the reason this makes sense is what we said earlier. The advantage of this is it maximizes the information. It takes advantage of the information from 1 to n minus p and from p plus 1 to n, which was the drawback of the least squares method. So we're going to minimize the sum of both of those, and that way we have taken advantage of the information that we possibly can. Now, here's where Burg comes into play. Burg showed how to minimize these forward-backward sums of squares while simultaneously obtaining a stationary solution. Interestingly, he did this in his dissertation but didn't publish it anywhere. So if you're wanting to look for the details of this, you have to go to his dissertation. We're not exactly sure why he didn't publish it, but that's an interesting little fact. Another thing that I wanted to bring up here was the fact that remember that the Yule-Walker estimates are always guaranteed to give a stationary solution. Well, so are the Burg estimates, but we'll see soon that the Burg estimates are much more stable, much more accurate in more cases than are the Yule-Walker estimates. And to conclude, this is how the Burg estimates came about. And remember that the Burg estimates, along with the least squares estimates, are the ones we mostly recommend. The least squares estimates are sort of known as the gold standard.